Alrighty, so what is happening? Attempting to understand our systems. About myself, my name is Beau Lyddon. I am a managing partner at Real Kinetic. I currently live in Boulder, Colorado, which actually usually looks like that. That's where I started Real Kinetic with a few friends, where we do consulting, talking about a lot of the stuff that you guys have heard the last couple days. I was previously at Workiva with all of the rest of us that were at Real Kinetic. There I was the head of platform architecture. All of us at Real Kinetic we were all leadership either on the platform teams or the infrastructure teams. So that's what we focus on now. Little PSA, I have hundreds of slides because I have a terrible memory. But actually I like to take them offline, so when I put these in PDF form, somebody else can follow my actual narrative. So don't actually try to read everything. I'll just tell you as I'm going. So if you feel like I'm churning and you're getting behind, don't worry. And as I mentioned, I have a lot. This is more of a 45-minute talk. So let's get going. Every company is becoming a technology company. Technology, especially software, is becoming a critical piece of every business. Hopefully, this is obvious. It's becoming more and more difficult to do our jobs without actually having an understanding of the technology. And here I don't really mean architecture diagrams, although that plays a part. It's a little bit of like Andrew mentioned yesterday, it's the why. Why am I doing what I'm doing? Why is the system behaving the way it is? How do those interact? And more importantly, it's not even just us in R&D. At this point, it's pretty much everybody. Our own team, peer teams, support and operations, management, R&D, leadership, marketing, sales, executives, board members, customer service, investors, auditors, customers. I presented to all of those within months at Workiva. That was pretty much my job. And providing understanding at their perspective is critical. All of them have slightly different perspectives and needs. No single diagram or even story will work. And I believe much of engineering leadership is about explaining our systems to the rest of the world. We need to quit acting like gods and treating everybody else like morons and start helping them understand our systems. And since we've generally sucked at this, the government and general population are starting to force our hands. They are finally realizing that software is eating the world and they don't really understand it, and it really freaks them out. Justifiably, by the way. As I mentioned, we have not done a good job helping others understand our stuff. I always use the example of my parents when they ask you what you do and you go, things, because you don't actually want to walk them through it. Unfortunately, that tends to be how we treat everybody. Right, Mark? So they are pushing back, as we know. And that's not the only place, right? We have the FBI dealing with encryption, Facebook, GDPR, compliance, you name it. And we watch the congressional hearings and we go, what morons, we should really be saying we failed. When all of those people up there not understanding systems, that's us that failed. We did not explain things to them. But now the cameras are officially on us. There is a massive backlash coming. As I mentioned, people are getting frustrated. Especially in the Valley, they are getting attacked. And they're starting to feel it. But here's the real kicker. Many of us have no clue what the hell our systems are doing. So we actually have to start with ourselves. We need to ensure that we can understand our systems and then work our way up and provide the tools that allow all to understand systems from everybody's personal perspective. This job is actually very, very difficult. I'm going to walk through why here quickly. Our systems are more complex than they've ever been, and they're growing in complexity. So I'm going to do a quick historical detour for the younger folks in the crowd. Go back to these simpler times where we had mainframes, Windows apps, client server, it doesn't really matter. These were all very controlled and constrained systems, at least that's what we tried to do, and it kind of made us feel that way. We did not have 24/7 uptime. We hardly ever released. Real time, I don't think we knew it was a thing. You may not actually believe this, but we ran reporting jobs on the weekends, at nights, printed them on paper. Devices, we told you what devices you were going to use. Seriously, like we did that all the time. Now, let's actually start with an architecture maybe from that era, and then we'll go through and add the new constraints and watch it evolve. So you get to check out my awesome Google diagrams here. This is a pretty basic client-server setup, maybe mid-2000s. This is the first job I had, basically exactly what it looked like. Transactional database, nightly backups to reporting database, that's where all those reports came from. And then customers and users started getting a little more needy. No more downtime. To support uptime, we need availability. To support availability, we need multiple machines. We need to start clustering. If we're going to start clustering, it's going to start getting slower, so we're going to start putting caching in front of it. Of course, those are going to be over multiple machines. Devices. We've got all the damn devices. We are talking to everything at this point. Real time. We went from nightly to I'm not willing to wait a second. I don't want stale reports. I want the answers in the data now, ideally visual, interactive. So we're going to set up these big data processing streaming pipelines, pass it out to a big data cluster. We're going to start having live reports generating off of all of that, connected to more freaking devices. We're going to release as fast as possible, from years down to minutes, seconds. And anybody can release for any reason. So we're going to microservice this sucker. And this is the only reason to do microservices. When you actually hit the point of scale where you need multiple people to release, so you're going to start isolating your systems around those boundaries. Do not microservice from day one. It is a cluster and not worth it. We expect access from anywhere at any time, so we better start throwing these out in regions. So of course, that's distributed again and thus slow, so we're going to throw some more caching in front of it. I haven't even mentioned infrastructure, so we're going to have multiple versions of that. CI/CD, and we've got ourselves the modern technology stack. The complexity has risen significantly. Don't worry, open source is here to save you. This is the cloud native diagram, or whatever you want to call this. This is all of the tools out there. Tyler mentioned all of the products. Here you go. This is what's out there. And they can help, but you need to glue them together using your own culture, your own processes. Obviously, not all of those tools are going to fit either, so you may need to do some of them custom, but there is some help out there, at least as far as filling in those gaps. It does not lower complexity. And I'm not done yet. There are significantly more nodes in the system, many connections between these nodes to handle scale. These connections create dependency trees. And even more, the nodes and connections are constantly changing because we're releasing constantly, all while we must maintain our usage rates. Thus, we end up with different versions of the same type of node potentially within a single request. So you've got a request going through your pipeline. You may hit the same type of system on different versions of software throughout that same request. All of this and more leads to our systems producing emergent behaviors that can't be predicted. The whole misnomer of I know what's going to happen to my system, that does not exist when your system hits a certain level of dynamic behavior. Behaviors are going to start emerging that you couldn't possibly have predicted. In other words, our systems are becoming much more similar to living systems. Cities, governments, economies. When you start kind of thinking about our systems the way economists think about systems, scientists think about systems. So this thing, kind of like alive, which, yeah, and it might actually kill us. So let's just go back to the old way. This is a mess. Except it's actually too late because this works. Beyond the obvious successful companies, Google, Amazon, Facebook, the research back up that these systems help all types of companies that embrace them across all industries. Dynamic systems that support rapid development and experimentation directly increase quality and velocity. Thus, ID becomes a differentiator and is no longer a cost center. So once again, back to Andrew's presentation. And DevOps is obviously a critical piece of this transformation. So in other words, if you don't have a dynamic system that supports experimentation and rapid release and embrace DevOps, you will be beaten by those that do. And if you want the proof, you can go get this book. They did a survey of thousands of companies. They've got it broken down by data. They have actual facts that you can present. And it's basically, it keeps coming up the same. If you build this system, you're going to beat your competitors, and you're actually going to be more efficient. And you're going to beat them in value. So if this isn't your world, it's going to be in the future. So what can we do to understand this chaos? So for this, I'm going to actually walk through some of our past experience at Workiva using a system we called Calc. This is the nonsensical paragraph from the patent on it. Really, it's just a distributed calculation engine. built on stateless runtimes with no SSH or live debugging. And this is in 2011, so yes, we were doing serverless quite a while ago. And not that SSH or debuggers would have mattered whatsoever, because we were working at massive scale. We had millions of nodes in this system. And to give you a little tease of some of the tools and diagrams we'll be looking at later, this was our calculation graph, which doesn't come through quite as well in the light here. But every one of those is a computation node, and then it's dependent computations, and they keep chaining out. And we had to create entirely new algorithms to track the complexity. They were dynamic. This is actually, if you start mapping your systems, it's going to start looking like this. So for us, the structure and thus behavior changed when the data changed. There was really no way for us to do analysis. When our customers made a change to their system, through their data, it changed the behavior of the system. So it's about as dynamic as it gets, which means you start asking questions like this. What is the state of the system? Is it done? What even is done? Is it broken? What is broken? What is fast? What is slow? A single actor in the system does not know the status of the overall system, yet there's no obvious way to track the status of the system unless the nodes within the system help us. To have any chance of keeping up with the understanding of systems, we need the systems to self-describe. And of course, we need automation and self-healing. This is too much for you to do. Even with writing scripts, you're not going to be able to keep up with this. And to have self-description, automation, and self-healing, we need data. We need the systems that give us data to provide necessary context. So now we'll actually get into the specifics of what we did to track this system. And we'll start by working our way up from the code. So the first thing we did, and the first thing I recommend everybody do, is pass a context object, basically everything. And what I mean by that is something like this. It seems simple, it seems trivial, it probably is the most important thing you can do. An example, and by the way, you probably already maybe do this, it's maybe in your code, especially if you're a multi-tenant application or a SaaS application. You probably have something like this going on. We had a guy on my team, he just started, we're doing a code review, he's got a function, and he's passing the user ID into it. And I go, I highly recommend turning that into a data structure. Almost certainly, you're going to start adding more data that's going to come through with that. And he goes, yeah, I'll do that next time. I really want to get this through. I'm like, fine, learning experience chance. 2 weeks later, I get the message, damn it. Now I have to go add an account ID. I'm like, yep, and I bet you before you ship, operations and infrastructure are going to start asking you for these other pieces of data like trace ID, request ID. And I'll get into more of those a little bit later here too. So what do we actually put on this context? So think about the data you wish you had when you were debugging an issue. So when you're actually in there debugging, and remember, you can't hook up a debugger. If you could hook up a debugger, what do you want? What is that stuff you're looking for? By the way, this is why devs should support their systems, so they'll actually do this. Think about the data that would have changed the behavior of the system. So an example, the user or company, time, machine stats, CPU, memory, et cetera, software version, configuration data, the calling request ID, any dependent request IDs. So then we can start thinking, what can we get for free? What can the machine provide for us? A lot of times they can give us the memory, the CPU. We don't really need to pass that along. The data we can't get for free, the data that's maybe more request specific. So we're thinking about a request tracing through the system. What usually goes with it? User ID is a good example. They triggered the request. Likely, somewhere in your code, you may have actions based off this. Are they an admin? Are they in this license pool, et cetera? Put that on the context. When you're debugging, you're going to want to know that. There are also some side benefits to this. If you're a SaaS company, you should probably also pass something like licensing data. This will allow you to move process around based off their actual licenses. Imagine routing traffic to specific queues based off user, account, license, environment. Amazon kills with this. When we set up our AWS accounts, right, we have quotas. Those quotas come through. Every single request, they check your quota. And if you're behaving badly, you go to the bad queue. If you're behaving fine, you get to stay in the fast queue. This is how they do that. This is how they do it dynamic. You go switch your quota immediately. You want to actually get that access. That can't go through a provisioning system. You need it now. So this is how they do that. So I highly, highly recommend starting to think that way. constantly would get calls from sales saying, hey, we want to start charging by usage. And we go, yeah, we just throw it all into queues and let it happen. And that doesn't really work. You're going to get killed by the company that does that because they will work at better margins than you will. And also think about things like GDPR and needing to track user actions data and what they have the proof system to do. There's a guy that writes a thing called the morning paper. He does computer science papers every morning. And he recently just did one on this. We are completely unprepared for what this is going to do to our systems. And adding this data, as part of the requirements of this is to understand why this user action became this data in this place. They want to actually have that historical trace of the data itself. And we don't do a very good job of tracking that today. So please use some data structure to pass contextual data to all dependent functions. This is the easiest thing you can start doing today. And then please actually log it out so you can have that data. And speaking of logging, structure your logs. JSON is fine. It doesn't really matter. Just get some structure to them. I am tired of writing regexes to scrape logs because we're too lazy to add structure at the time when it actually makes the most sense. We're in there writing our code. We're like, screw it, big string of crap. And then you're in debugging and you're going, oh, crap. Once again, imagine you have thousands of logs. When we're doing these systems, these traces, when you're in a microservice environment or a service environment, you don't have one big stack trace. You have hundreds of stack traces. And they're going to be out of order. They're going to be interleaved with other stacks. How are you going to get the ones you want? You need to be able to say, give me all of the stack traces for this user, for this request. I really don't want to write regexes and bash scripts to do that. So you want to end up with something like this. Once again, just get it to something like this. JSON works, whatever. Get that data in there, get it structured like this, get it into your logs. And you can take this as far as you'd like. You can go very structured with a type system, code reviews, et cetera. This is what Kiva did. We were hardcore about this because we did not want to have things like passwords being leaked into the logs. So we had a whole review process for how you actually logged out. And we also wanted standards. If you're going to log the account ID, I want you to log it the same way so I can query across the systems. If you have hundreds of teams, hundreds of individuals, ideally they're logging the same way. By the way, there are many existing libraries for this. Just Google your language du jour and structured logs, and you'll probably get something, at least as a starting point. Like I said, as minimum, just get them into a format with some sort of property tags. Now that you have the logs, you have the context data, now you need a data pipeline. There's a ton of data that you want and need to collect. This isn't just logs, it's metrics, analytics, audit data. It's just going to keep coming. We want to make it as simple yet robust as possible. Most importantly, we want some system that has all this data. So what we often see at the beginning, something like this, client devs are console logging, service people are tailing some logs, database guys are tailing their logs. Hopefully, ideally, before they get to production, maybe they've switched to something like this. And then inevitably, we start adding. It's like, well, we got to get some Nagios, we got to get some alerting, got to get the audit system, we got to get the BI system. And now your service is spending more time with non-critical path dependencies than those on the critical path. What I mean by the critical path is the action the user actually wanted to do. You know, we're spending more time talking to all these systems, getting the metadata out, than actually just doing what they wanted. So let's standardize and simplify this. Let's get it to a single data pipeline or queue. You can use a pull process. It doesn't really matter. Just have a single standard way to do this. So what we did is we used a log-based queue. We used Amazon Kinesis. All of our logs, all of our data went into Kinesis. We also use something called a sidecar. Today there's FluentD. At the time we did it, we actually had to do something custom. FluentD wasn't around yet. This allows you to write to standard out, and the sidecar will actually just take care of this for you. And this, especially in a container environment, this will be pretty critical. Sidecars are something that's going to be very common moving forward. And developers love it because they don't think about anything locally. Just log in a standard out like I always do. Data pipeline provides a layer of abstraction that allows you to get data everywhere it needs to be without impacting developers in the core system. Some people may go, yeah, that's a lot of crap. We talk to all of those, and more, by the way. So where should all of this go? At minimum, it should go into a cheap long-term storage solution. Get your data into Glacier something. Get it into somewhere. You'll want this for historical system behavior to help machine your system into automation. Once you're like the masters of this domain, you're going to start having that data do all of the stuff you're doing. I don't know if you guys know about a thing called circuit breaking, where you have your network calls kind of handle different latency loads. They might do retries and all of that. Now imagine hooking that up to historical data so they can be smarter about it. So you go, normally when I'm seeing a latency spike here, this is what happens. So maybe I can automate even how we react. And the system will actually start, and this is when we talk about self-healing. You don't want to just blindly do crap. That's where we get things like the thundering herd, where everything's going to drop for 200 milliseconds and then maybe 600 milliseconds. Well, congratulations. Everything's doing that at 200 milliseconds and 600 milliseconds, and your system's still going, oh. Over time, your system will learn that behavior, especially service to service. Services don't behave the same way. Each of them have their own independent behavior. And it's going to change faster than you keep up with. Ideally, all data should go into a queryable large-scale data storage solution. Hopefully, they have some good time-based querying capability. And BigQuery, Redshift are good examples. And this is why we structure our logs. There are also more targeted or customized solutions starting to fill the space. This is Honeycomb. This is from their marketing material. Start solving high cardinality problems in minutes. High cardinality refers to the columns with values that are very uncommon or unique. An example would be a data column with a high cardinality would be users with a user ID. Once again, that's what I was talking about earlier. You're going to be able to query all of those requests. You need to say, give me everything for a user and a request. You start thinking like scientists, like data people. Query anything, break down, filter, pivot, high cardinality fields like user ID. Once again, that's why we structure our logs. We want to see the raw data behind every result and see the exact events leading to an issue as affected, who is affected and how. We want to share those queries results in history. We want to collaborate. That's all from what Honeycomb provides. This is once we need to start thinking like that. There's many other options out there. All of these vendors are converging into the same world. The beauty of a data pipeline is you can use one or many, test multiple in parallel. At Workiva, we were testing 4 or 5 different log providers in parallel to figure out what we liked best, and the engineers had no clue. Although I will also say the engineers are your users, so if you're treating it like a product, use them as user testers to make sure they actually like the logging system. That was one of the problems they had at Workiva, is the first one they chose, they didn't talk to the engineers, and they hated it. And no matter what you do, you're still going to end up with multiple consumers. We can't keep up. Crap's changing too fast. This gives you that layered abstraction. So as things are changing behind the scenes, it doesn't impact the core system. So back to that structured logs thing. Structure and standardize all data leaving your system. Provide libraries to add structure, not just logs, but also metrics, audits, everything. At Workiva, we had one standard across the board. If you want to, you can break them apart by type. Ours actually had like an inheritance system. So everything had like the user and the account, and then it would inherit based off the type of system. So we get more precise the more precise the system they were using. But most importantly, just get it standardized across your services, those base data values. But people are also quickly realizing this data is all related, and the separation is kind of arbitrary. It's this thing called open census. This is a tracing library. It's actually tracing the metrics. Open tracing was the tracing standard, and then they thought, all the tracing data is the same as the metric data, so let's just now do open census. I don't think they'll stop here. I think there will be more layers once they realize all of this data is important. And as I mentioned, most of the infrastructure data players are converting to support all styles of system data collection. All of these guys are going to the same place. Only a few of them will survive. This is another reason to have a data pipeline. This will help you support whatever comes next. Next, minimize, isolate, and track dependencies. Unmanaged dependencies are where throughput goes to die. I'm not a big fan of Golang, but they did get a few things correct. One of them is promoting code duplication over introducing unnecessary dependencies. Personally, I kind of like more the Golang plus Haskell approach, which is a dependency can be introduced when it's well formalized and worth the cost. Haskell, you try to get everything into a mathematical law. Mathematical laws tend to not change, so you know that dependency is pretty solid. I'm not saying we got to get to law level solid there, but you want dependencies that aren't going to change every 15 seconds. A quick note, avoiding dependency does not mean build everything. The Java padding library is not the same as using Amazon Dynamo. Dynamo and a client library has less code and likely no additional dependency versus doing something from scratch. The padding library is a waste of time. Also, this is way better than building your own database, even though half the clients we work with think that building databases is the way to go. Anyways, back to what we're doing. If you're going to introduce the dependencies, then clearly track and pin them. Ideally in a single file in the project or repo or an aggregate repo, just make sure you get them tracked and pinned. If it's possible, standardize the spec. Each language maybe has its own. Ideally, you'd like to have a superset, but as long as you have a system that can take the subset into a superset, that's fine. Then create a process that aggregates those dependencies into an overall mapping. This will start to give you a picture of your system. This goes for all services as well as libraries. So not just the libraries, but the services you're talking to, track and pin. Get them into a file where you can track that. Then you get free architecture diagrams. So when we start having these pinnings, you can start looking at things like this, where you've got library version 1 to version 1 to version 2, using another service that has libraries of this version to this version to this version. But then we can start visualizing that over time, so we can start to see that actually transition through time. We can actually see. This is the declarative dependencies of our system. These are what the engineers think is actually happening. So this is a good starting point. And we can start to graph all of this out. Netflix has some great examples and tools. These bastards are always leading the charge. This thing called Spigo, I don't know. And SimianViz, Adrian Cockcroft, who's actually now at AWS, created this tool. And they did it more for their services, because that's a small slice of Netflix services. I highly recommend Googling Netflix Death Star to see what their actual service setup looks like, because your brain can't comprehend how many they have, and this is why we have to start thinking this way. That said, service network dependencies are still a nightmare. So we're back to sidecars. Use network sidecars, or they may be called service meshes or proxies, to better isolate and handle these dependencies. Similar concept to the data pipeline. Here we have our services. We're going to throw up what we call a network proxy or network sidecar. In this case, we're going to use Envoy. This allows the engineers to do is just pipe all their traffic to port 80. They love to do this. And then you're like, no, we need SSL. Envoy allows you to just stick that in there and go, yeah, do to port 80. Don't mess with any of that crap. Don't mess with search. Don't do any of that. This will take care of that for you. Then it also includes service discovery, et cetera. So it's a combination of many of kind of the networking things we do today, API gateway, proxies, routers, a lot of those same solutions. And they give you things like load balancing, service discovery, health checking, circuit breakers, standard observability, and tracing. Using sidecar allows you to easily standardize without introducing new dependencies at the code and team level. So a lot of people try to do a lot of what was on that last slide via libraries. It allows you to get rid of that whole thing. They get to use their little simple networking library, build into a language, pipe it out, and this takes care of it from there. And of course, that same metadata that they're tracking, you can actually put back into your data pipeline. So we're pumping the data out of Envoy back into our data pipeline. And Envoy, these systems let you do cool things like pattern matching. You can do security routing based off the patterns, different security based off the routes. It's actually pretty impressive. A note on that is pretty immature. It's changing quickly, so it's worth looking at, but it may not be stable for you yet. But you should still, if you look at doing something like it, at least use it as inspiration. And there are many other tools, especially around Kubernetes. They vary from service mesh focus to the whole damn thing. Istio, Linker, Kong, they're coming like crazy. Just like the data providers, thousands are joining, few will survive, and we'll just see what happens. All of these come with free monitoring tools and distributed tracing. We need better ways to visualize our systems. Charts dashboards are nice for looking at a system behaviors in a generic data-driven perspective, but that layer of abstraction, while helping isolate variables, removes a layer of intuition. It doesn't really give you a feel for anything. We need the ability to also visualize specific and aggregate behavior, and tracing is an example. I'm going to go through some code real quick. This is just a function that calls 3 other functions. For some reason, it's slow. It just feels slow. So we throw in some crappy timing metrics, and it says it's slow. But instead, let's try to use tracing. So we're going to use that context we had with a trace ID, and we're going to trace this function. This is similar to what you can do within a process, but this is actually cross-process. And we're going to drop those traces on the child functions, too. And what this is actually doing is taking a trace ID and then building a hierarchy. The top-level trace ID becomes the parent trace ID for the child functions. Now you have a graph, a call graph. Looks something like this. Now we have my function. Now we can start to see what our code is actually doing. And since we're collecting all the metadata as well, we can actually start to add some stuff. So this is back to those big, ugly things I had earlier. This is what we were doing. They weren't just every dot the same. Those dots were actually telling us something. The larger the dot, the more the dependencies. In this case, red means this errored. Green means it was moving, or the darker green means moving a little slower. It's a little latent, right? You can start to use that to help you get an intuition for how these processes are actually running. And we realized these aren't even pure functions. They're all doing I/O, and we didn't even know it. This is the type of thing, we actually see this a lot, especially with people using ORMs. They don't even realize they're making database calls. Then they're like, why is it slow? This visualization does do a good job of showing dependencies, so back to this. This is what that was. But it's not great for all needs. In our example, these are synchronous processes, so they're actually like this. This style isn't as intuitive for the actual performance within the process. So this is actually what a standard tracing view would look like. So now you can see. We call this the waterfall view. So when you start seeing this, your shit be slow. You need it to not look like this. So this is an example taken from Jaeger. There's an actual tracing tool out there, and you can start to see that. With those lines block on top of each other, that's good. You're doing things asynchronously. And they come with the ability to search, do all sorts of stuff. These tools are really, really powerful and basically required in a microservice environment. And tracing standards and systems, just like the other stuff, are quite immature, but growing and hopefully stabilizing quickly. I need to go quick because we're out of time. This is where open tracing, open census. There's the W3C now has a distributed trace context community group. I highly recommend joining that. So basically, there will be tracing as part of your HTTP headers. So just pick something. Doesn't matter. Keep going. Here are some of the tools out there. Jaeger, Zipkin, Amazon X-Ray, Stackdriver has it for Google. And as I mentioned, all of these guys are starting to add it too. Everybody's doing the same thing. But any system that lets you query and aggregate relationships will let you do this. So even your database will let you do this. Just a query creates a graph, and then you get to throw the visualizations on that you want. Like these good old Netflix people again. They create a different, they run at scale we can't comprehend. So they actually have, this is their network traffic. And those little dots, red dots, are things saying there might be trouble here. Doesn't tell them what the trouble is, just says maybe trouble. And they start going deeper and deeper and deeper in to learn that. This is, once you start getting at scale, it's back to the perspective thing again. And this is similar to one we had earlier. And you can see that sucker's doing something. That is doing a lot of traffic. It starts to give you some visualization. It starts to give you an intuition to what your system's doing. So we also want to provide the ability to trade through the system. Some people call this a tracer bullet. This is really saying is we want to be able to get requests going through your system without actually doing any destructive operations. Don't write to the database. I want to get a request going through that just flows through. It's kind of like if you're getting a MRI, right? They put the injection in you and it flows through so they can see it. That's what you're doing to your system. You're doing your system an MRI. So in other words, send the request, no ops, doesn't write to third party. This is how Amazon tests all their APIs. Once again, you can use your context for this. For something like a request type on your context, standard request type, trace, whatever. Come up with something that lets you know what your request types are like. And then your code, you can have something like this. If request type is a trace, don't write. That is, and yes, that looks like a feature flag. Yes, use feature flags. You can use them for more than just features. Feature flags are good. They're good for a lot of things. That is literally how we created our diagrams. That would have been millions of data store writes. We don't want to do millions of data store writes. So we just trace through the system. It costs us computation, not writes. Like I said, get this on your context because you actually want that to be part of the data. So when you're querying it later, you know what context it was running within. Probably not good if you have data store writes when you shouldn't have. So you probably want that in your debugging statement. As I mentioned, this is how we did this. All right, I'm going to go really quick here because now I'm going to get ranty. Provide the ability to experiment and test in production. Tracer bullets, feature flags, all of this. Do crap in production. We should also support tester accounts, especially if you're already a SaaS company with multi-tenancy. Why don't you have company accounts to let you act like your own self within there? All of the work you need to do to support work, to support your devs doing work in production is all the work you need to do to support multi-tenancy. The ability to isolate services, accounts, actions on demand. So if you're worried that your devs are going to screw crap up, what makes you think your users aren't going to screw crap up? They're no different. So if your devs can screw crap up in your environment, then your users can screw crap up in your environment, and that's good. It's back to what Andrew mentioned yesterday. Things are going to break, just handle it. The ability to stop, interrupt, move bad services, that is key. Ideally support chaos tools in production. If your users and your devs aren't breaking it, you start breaking it up. If you do this, you will be so much better off. Allowing folks to experiment and learn within a production system helps them build an intuition for the only system that matters, which is your production system. Use tools custom, if necessary, to simulate usage, load testing, chaos, general, traffic simulation. Network proxies, that Envoy in that, they will actually capture your traffic. You can store that and you can replay it. You can replay the same traffic. I replay the same traffic in production, which you can then replay, exactly, and then start killing environments. Tyler, who presented this morning, has a blog post out this week that basically goes through this in deeper detail. The more important, the easiest thing to think about this, less environments means less environments. It's less crap to maintain. We can spend more time on the only environment that matters. So why do we spend so much time not in production? We know replicas and models are not as good as the real thing, yet we continue to do everything based off replicas and models. Worse, we allow shortcuts in other environments that won't work in production. We let use SSH in dev, but not in production. Wouldn't you also want the same tools that you can use in production? We don't invest in building production-capable tools for dev because reasons, I don't know. Instead, you're going to wait until you have a production issue, and I see this all of the time. What are we going to do to resolve it? Well, not much. Normally I would do X, but I can't because those only work in dev environments. So I'm going to attempt to hack together some duct tape solution that I'll never use again. I'm going to run it now in production without getting it through a code review process. This is basically standard practice for many companies. It's crazy. If you've done everything we've mentioned previously, you don't need the other environments. Unless, little note, you're doing massive things. Then you can stand up another environment for that. But if you're doing these things, and by the way, Netflix, Amazon, all of them, everything in production. Do your best to force as much development testing to production as possible. So in closing, there is just tons more I didn't get to. But really, it all starts with empathy. We need empathy for our peers and our users. I would love to talk about this further. If you don't want to talk to me now, I'm on Twitter. So quick recap, pass context, structure your logs, data pipeline. Structure all of your data and give it to the pipeline. Minimize and track and build visualizations for your dependencies. Leverage service meshes. Distributed tracing. Support no-op, experimentation, simulation, and production. And then kill everything that's not production. And here's all those tools again. I will put these slides up, and I'll actually have references to everything. It's not really possible to get to everything, but I'll get them on there. So thanks.